Oh, we had the nuclear accidents. And holy smokes, you guys are quick today. Good morning. I got Aslan, Kai, Alessia. Great. I've got Inessa, Hannah, and Kiara. I've got Matthias, Alessandra, and Clara. Yes, I've got Amelie, Aaron, and Isaiah. I've got Felix, Ethan, and Timothy Peduso. Great, keep them coming. I've got Leo, I've got Malta, I got Zach. Good morning, all of you. Leah, Malta, Zach Dye. Great, I've got Timothy Hartling, I got Linus and Ayala. Timothy Hartling. And Steve, Linus, I got. Good. I've got Lauren and Jack and Cassidy. Super, and I've got I got Isabella, and I got Sina. And I've got Iveo. You better tell me who you are. Iveo, who are you? I got Corsine and Julius. And Anton. Good. Oh, I got a message. Yes, Alessia, the math physics elective would be nice preparation for the physics in 11th and 12th grade. I fully agree. So do it. Do it. Liam, good morning. And Paul and Alicia. Great. Okay, folks, let me just check and a few more. Isaac Feldman, are you out there? Devante, are you out there? And other than that, 9E is complete. Woo, go to town, 9E. Let's see how 9F's doing. Looking for Stella Brass. Looking for Ingrid Hicks, Corey Kamak, Sophie, Avram, Allie, Michael, and Charlotte. If any of you are there, there's one. Sophie's there. Hello? Hello. Does it cover? It'll cover different things, Alessia, and I don't teach it. So best is if we ask Frau Müller, what is it about. She's really friendly, quiet but friendly. Ask her and she'll be able to tell you. Type her an email. Write me if you don't know her name, okay? Who else? Sophie. Yeah, welcome, Sophie. Okay, good. All right, let's see what we're doing today. You ready? We got 3 things. We need to finish up talking about nuclear waste. We need to do some reactions. I forgot we haven't done that yet. That's important. And then we need to talk about nuclear reactor accidents. There have been several. 2 have been fairly dangerous, and we'll see what those are about. Good. Thank you, Charlotte. She is here. I'll put these aside. My people, if you have a periodic table, please grab it. You'll need this today, your periodic table. Thank you. And Devante is here. Good. Nice. Okay. I'll leave those on the side there for now. And we'll catch some other folks when they arrive. Okay. When last we met, we talked about nuclear waste and we talked about high level and low level nuclear waste. What we didn't talk about yet was time. Okay, one problem, I'm going to say nuclear waste problems. There's at least 2 I can think of. So, my people, let's see how awake you are this morning. What do you think are 2 potential problems with nuclear waste? Even if it's away from people, what are 2 other problems with nuclear waste? See if you can guess at least one of them. So brainstorm a little bit with yourself. What might be 2 problems with thermal pollution? No, that's coming. That's a different form of waste. That's not the actual radioactive stuff, Alessandra. That's the warm water coming out of the cooling tower. And that's not necessarily related to the waste. Earth, I don't follow you, Kiara. The waste could affect the environment. Yes, could you be more specific, Zach? Used uranium still radiates a bit, probably. Yes, good. But there's another aspect, Leo. Keep thinking. Hard to contain. Yes, in a way. Recycling, no, they can't really do that, Paul, unfortunately. Thermal pollution, no, that's coming from the cooling tower. Radiation, it's radioactive. Yeah, I already said that. That's not the point. Okay, Kiara's got it. It goes into the soil and the earth, or it can. And Isabella has the other. It takes a long time and it's hard to store. Thank you very much, Isabella. Good. All right. And Hannah has hit the nail on the head. Okay. It can get into the water. So here's the deal. Generally, nuclear waste is stored underground. The problem is if water gets in there. Oh, I got an Avram. Avram, good morning. Let me check you in. I've got an Avram. Thank you, sir. Okay. So the problem underground is you don't want water to get to it. And so that's, as Hannah sort of guessed, a problem. So needs to be dry. So storage area. And generally it's in rock, like drilled out rock. It could be caves, but generally it's drilled out like an old mine. So storage area in rock must be dry and no groundwater passing through. Groundwater is under your feet, right? You know that, I hope. So underneath your feet, you've got water flowing in the ground. So you don't want this happening where you store nuclear waste. You don't want the groundwater to touch nuclear waste because then the groundwater gets contaminated. And you and I drink that stuff. So that's not a good thing, right? So we want to keep it free from radioactive contamination. And the other thing was, I think Isabella said, it just takes a long, long time to stop decaying. So it's radioactive a long time. So it's got to be stored a long time. So we're talking about storage for thousands of years, okay? The old bad joke is love may not be forever, but nuclear waste is, or darn near, okay? So that's a problem. You've got to find a safe place. And who knows what this means? NIMBY. What's NIMBY? NIMBY. What does NIMBY stand for? And then we'll be done with nuclear waste, but that's a real problem, is NIMBY. Ooh, it's a really good thing for everybody to know. NIMBY is a Kurzung, an abbreviation for not in my backyard. See, NIMBY. And what that means, exactly, good. So what that means is that nobody wants nuclear waste in their area, do they? Nobody wants it, like we don't want it under Berlin or whatever. We don't want it in our area. Nobody does, but it's got to go somewhere, right? Someone has to take it. All right, and no one wants nuclear waste in their area. Good. Any questions from you or comments about nuclear waste? Okay, Devante has one. Why don't they just shoot it into outer space? They could, Devante, but the problem is two things. The amount of money would be, no pun intended, astronomical, and the amount of weight of stuff that they'd have to send in space is just too much. It's too much to fit on a rocket or 100 rockets. You know what I'm saying? So it's just not a practical solution. Otherwise, that would be a possibility, but it's too much, Devante. Good idea, though. Thanks, Hannah. Glad somebody's listening. I think so too, Sophie. We're sending it out there, and maybe it'll come back down into another country, or maybe it'll go to some other nasty place in space and just sort of pollute outer space. It's not really a good idea. We need to take care of our garbage here. Good. Thank you for the comments. Any other comments or questions about nuclear waste? It's an issue your generation will have to deal with. Interestingly enough, Germany accepts nuclear waste from nuclear power plants in France, since Germany shut down all of its nuclear power plants after Fukushima. Okay, before we do nuclear accidents, let's talk a little bit about reactions. So I want to talk about fission reactions, okay? Somebody give me a common fuel for nuclear power. We've had two we talked about. What's a common fuel for nuclear power? No, I guess we only talked about one, but there are two. Exactly, Timothy. Right. Germany doesn't have nuclear power anymore. Yeah, I don't know when the first power plant was started in Germany, Kiara, but they closed down in 2011. Yeah, unfortunately, Alessia, they can't burn nuclear waste because the radioactive elements don't burn like most are metals. So they would just go into the air and still be radioactive. Okay, I got it from Leo and Ethan and some others there. Thank you. And Kiara, I got uranium. Plutonium also will work, by the way. Let's take uranium. And I'm going to say it's 235, typical fuel. Remember how we did this? So I got a U, I got 235 for the mass number, right? And I got 92 for the atomic number. Allie is there. Allie, you got to tell me hello so I can check in. Allie is here. Thank you, Allie. And you got a question too. Let's see. As is Corey. Would it be safer to use thorium? The problem with thorium, Allie, is it doesn't give off enough heat, so it doesn't heat the water enough. It's just not radioactive enough. Okay, Corey is also here. Thank you, Corey. Still missing Ingrid and Stella and Michael. Still missing Isaac. Okay. Remember, what's going on is I've got a big nucleus. So remember, this is the deal, right? I'll just draw it one more time. There's my nucleus. What am I shooting at it to split it? Who remembers? What am I shooting at the nucleus to break it up into pieces? So what's the bullet that splits a nucleus of uranium? Thank you. Alessia has it. And Lauren, neutron. So I'm going to shoot a neutron here. Ready? So that's going to go and split this sucker into pieces. But what that means for my reaction is we're going to go plus a neutron. A neutron looks like this. It's N, and we put a little 0 up in the corner because it has no charge, right? And then we can put a little 1 down here and a 1 up here because it's got 1. Wait a minute. Boop, sorry, that's wrong. A 0 down here because it's got 0 protons because it's a neutron. But I got 1 up here because that's the number of protons plus neutrons, okay? Oh, a lot of people knew that. Thank you, folks, for jumping in. Liam, Linus, Sina, and others. Good. Let's make this thing now break down into parts. Usually it's 2 main pieces. I'll be really honest. It's seldom anything but. So I'm going to make something up because I've done this enough. So I'm going to just say one of the pieces this time will be barium. And that is, I think, number 56. Yep. And it's going to be, I'll say 140. Now, so here's my process, right? So this thing splits into pieces, the nucleus. We're going to fill in this in a second, okay? Here's, let's say, the 2 pieces. But to keep a chain reaction going, and I think some of you told me this before, I can't remember who it was. To have a chain reaction going, what else has to come off here? So I got two big pieces. One will be uranium. We'll fill in the other in a second. But what else has to come off to keep the process going so that I can achieve critical mass, right? Or in this case, so I can just have a chain reaction. A neutron, thank you. Or a couple of neutrons, good. So they can make more neutrons, good. Thank you. And I see Ingrid is there. Thank you for checking in, Ingrid. Okay, so in addition to these guys, let's have a couple neutrons fly off. Okay, so those are the pieces flying off, okay? Plus, plus 2 neutrons. And plus, to be honest, it's not a chemical, but plus a lot of energy. And that's the energy that we're interested in. That's why we do this whole process. Okay, let me write down first. I got my Ingrid. Okie dokie. So, my people, this is a typical problem. You ready? We're going to figure out what must be, let's say that is the barium. We got to figure out what the other thing is. We can do it by using subtraction, can't we? So here we go. Do this mentally with me, and then I will have you try one afterwards, okay? Here we go. I got 92 protons. That's it, because that's just a neutron. And I got 235. Nope, I got 236 neutrons, right? Because I got one here plus 235 here. So that's 236. Go to the other side, do a little subtracting. Let's do the protons first, because that's easier. 92 minus 56. So what'll be the proton number for the other big chunk? So who can do that in their head? 92 minus 56. A couple of you had that already. Good. Thank you, Alessandra, Ingrid, and you guys are tops, and Timothy as well. So it's 36. And you can look up and see who that is now. Element 36 on your periodic table is who? Is who? And a couple of you had it. I think Alessandra had it already, and so does Aaron. It's krypton. No, that's not kryptonite. Don't worry about Superman. It's Cr. It's a gas. But we don't know the top number. Let's figure it out. Okay, ready? Other side, 236. This side, we got to subtract these suckers. So 236. I got 140. I got it till we get, but I got 2 more neutrons here. So I got to take away 142. So ready? I'm going to do it up on the top here. So I got to go 236 minus 142. 140 plus 2 neutrons. You got that? So what's your top number? Can somebody beat me? 235? No, it's 235 plus 1 more. There's another neutron. Don't forget that one. So 236. It really is 236. I got 2 answers, 93 or 94. I think it's 94. So it is. So that number goes here. Right? So 94 is the isotope of krypton. That would be the answer here. Okay, ready? Your turn. Your turn. Here we go. Let's say this time we use plutonium. So we're going to go Pu, which is 94, and 240. We're going to hit it with a neutron again. And let's say we get argon. Argon is 18. And let's say we've got 42. Plus 3 neutrons come off this side this time. Okay, I'm going to give you a little time to fill in the blank. How did we get the BA? We looked up 56. Oh, how did we get that? I knew that. I knew that. So that's how we got it, Kiara. Yeah, I gave it to you. Thanks, Alessandra. Okay, so I'm giving you this time everything. Fill in the blank, everybody. Type it in when you get an answer. So do the subtractions, figure out the numbers, and what element it must be. Good, I've got some answers already. Let's see if others agree or not. Okay, so I got some numbers here. I got some guesses. So this time I got 94 minus 18, which would be 76. Good. I believe that's right. 94 minus 18. Yeah, 76. And that is OS, osmium. But I still need the top number. Looking for the top number from somebody. So work on getting the top number. Thank you, everybody who got 76. That's good thinking. I'm glad. Liam, Timothy, Peduso, Kiara got that, as did Paul and others. OS. Ethan had that as well. And the top number, oh, you guys are so quick, I can hardly see it. I got 198 or 196. We better agree here. Be sure you subtract 241, right? Minus 45, I think it's got to be. 42 plus 3 more. So 241 minus 5, and I'm thinking 196. Sophie and Devante, looks good. And Tim Hartman as well. So 196, and good job. Thanks, everybody. There's so many of you, I can't read everybody's name. You guys are awake today. That's great. Questions from you about how to do this? This is a fission reaction. Oh, and I forgot to say, of course, plus energy. How about En for energy? How much energy? I'm going to give you a number. Let me give you that number now, just as an amount, okay? Relatively speaking. By the way, there's lots of different possibilities. Not an infinite number, but lots of possibilities. So this is only, for uranium, this is only one possibility. One possibility of many. Okay, now let me go see how much energy this is. I got it right here on my folder. Okay. Here we go. So it's about, I'm going to put a little star here. So energy is it's about 1.9 times 10 to the 10th kilojoules, and that's per mole of uranium. So think about it. Uranium here is about, well, look at the isotope. If I had pure U-235, a mole of it would be 235 grams, okay? So that's like a fourth of a kilo. So you can hold that in your hand. That much, if I could like have it all go to fission right away, it gives off a lot of kilojoules, right? candy bar would have like a couple of hundred kilojoules. You know what I'm saying? This is 10 to the 10th kilojoules. So nuclear energy really gives off a lot. Okay, did we do something wrong? Let me look and see what the commentary is. How did you get the top number again? So let's see. We got a good, we said 240 plus 1, right? So 241. Yeah, minus 42, minus 3, and then you got what's left. Yeah, 241 minus 42, and then minus 3, and then you get what's left over here. Generally, Charlotte and everybody, the numbers on this side got to add up to the numbers on this side. That's really the secret, isn't it? That's why we have to subtract sometimes to do it. I hope their explanations help. If not, ask again, Charlotte. Any other questions from anybody on how to do nuclear reactions? And now you have a rough idea of how much energy that is. A lot of energy. Yeah? Okay. Let's talk accidents. Let's talk accidents. Nuclear accidents. There's been at least 4 that I know of. Yeah, add and then subtract. So, Kiara, first you add, then you subtract, right? It's the only way you can get the missing spot in the blank. Add, then subtract. Okay. Okay, so nuclear accidents. 4. The first one was in the 1950s. It was called Windstar. And it was and we're not talking about nuclear bombs, we're talking about nuclear power plants. Windstar nuclear power plant. And that was in England. Bet you didn't know that. The first nuclear accident was in England. The next one was in the US. It was 3 Mile Island. You might have heard of that. It's in Pennsylvania, if you're familiar with the US. And that was also a nuclear power plant. And I should give you some dates. This is 1950s. You can look up the date. This is the 1970s. And this is, sorry, the next one was Chernobyl. Chernobyl power plant. And that was at the time it was called the USSR. Now it's called Ukraine. And that was in 1986. And then we had good old Japan with Fukushima nuclear power plant. And that was, it was 2011. So you can tell. Okay, thank you, Ingrid. Thank you. Alessia knew some of those already. That's cool. Right. And thanks for helping each other there. I'm sorry I didn't take the time to work through another problem, but I'm going to leave these two, the first ones, but let's talk about Chernobyl a bit and Fukushima, okay? First off, Chernobyl. Where to start? I'm not going to write this, but Chernobyl was the result of a training exercise that went really wrong. They tried something more or less at a time of day, luckily, when there weren't a lot of people there. And yeah, the Chernobyl accident was caused by human error. Human error. Essentially, the fuel got too hot. Can I just say that? Uranium fuel got too hot because they screwed up. The control rods didn't drop quick enough, and they may well have turned off the control rods because this was a society that did not take a lot of protections for human beings. So uranium fuel got too hot, TOO, by the way, and the fuel melted. And control rods could not drop. Just as a reminder, there you can see the whole thing. I do want you to take notes. Everything I put on the whiteboard should be in your notes. I had one student comment at parent teacher conference, oh, we don't have to write on that, do we? Well, duh. Okay, it's the same as at school. So please take notes as you normally would with me. Thank you for doing that. And Inessa's back. That's good. Yeah. So Chernobyl, because it was in the Ukraine, was close enough to Europe so that Germany, especially Eastern Germany, where you and I are, got a lot of radiation. So people were told to keep indoors. People were worried. They couldn't harvest the crops that year. Okay. Serious stuff. Okay. And what happened was essentially the thing blew up once we got not the whole plant, but one of the reactors blew up. Yeah, some of the yeah, one of the exactly, Hannah. One of the managers of Chernobyl was sent to jail for violations, but really he was just like a sacrificial lamb. The whole government at the time, the USSR, allowed a uh, uh, a feeling, Hannah, of okay, if there's no safety, it's okay. Everything will be okay. They did not have a good safety culture, so the plant manager really wasn't that, you know. Hey, Allie, if you write absurd again, I'm going to erase you from the comments, Ali. So participate well or don't. All right. Okay. So much radiation. Yes, it was a lot of radiation. Okay. So, what can I add here? Human error. Uranium fuel got too hot and fuel melted and control rods could not drop. The reaction, let's say the reactor core, right, where the fission takes place, blew up. And fuel burned for days. They were afraid the fuel was going to get into the groundwater. Luckily, after a few days, or it might have been weeks, I don't know, I have to look it up, the fuel stopped burning. It cooled down enough. Okay? So, yeah, probably, Alessia. Yeah, exactly, Liam. The people didn't care. There were a lot of safety features at the Chernobyl nuclear power plant that were turned off. They were turned off. For example, flooding the fuel with new water to cool it down. They had turned that off. It was stupid. And they paid a big price. You better believe it, because there was a big atmosphere of secrecy, but not a good atmosphere of safety. And if you have secrecy first instead of safety, you have problems eventually when something goes wrong. Okay, so several people died directly trying to clean it up. Probably hundreds of others got cancer over the years. It's still a radioactive place today in the Ukraine. And it's covered with a big building. They call it a sarcophagus, which needs to be replaced. And they might have replaced it by now. I know they're going to do it around this time, because they don't want it's still open to the air, and they don't want more radiation coming up into the air. So they have it covered with a building. So it's still a danger today. Some of the fuel, hundreds to thousands of years until it goes through enough half-lives so that the fuel will not be a danger to fouling the air. And you can't live in that area, okay? Interestingly enough, you can visit the area briefly as a tourist. I would not do it, but you are allowed to do that because you get radiation for only a small amount of time, but not in my interest. If you want to do that, you could, but I wouldn't advise it. Okay, that's Chernobyl. We're going to see why Chernobyl blew up and why the next one blew up as well, which is Fukushima. How we doing on time, people? We got 5 minutes. Well, we might get there. Ten years ago, so you guys won't remember, but anybody read about it? What happened at Fukushima that caused a problem with the nuclear power plant there? Anybody know for grins what happened at Fukushima? It wasn't a human error per se. Yeah, there was an earthquake, and Kiara, it caused something else. This was built right on the coast. This was built. There you go. Thank you, Hana. Super. Hana knows about this stuff. A tsunami hit. So the earthquake caused a tsunami. Caused tsunami. So a huge wave of water, which, you guessed it, knocked out the ability to lower the control rods. So it knocked out the power. Therefore, the control rods could not be lowered. You can see how important those are now, can't you? Could not be lowered. The fuel got too hot, and we'll see what happened. And reactor core exploded. I don't know if they've cleaned that one up today, but I think they've opened the plant again, believe it or not. So I think some of it is still working. One of the cores exploded. I think the others did not. So what is about this exploding? Let's talk about what's happening. I don't want this to be mysterious with you. I still got 2 minutes. Let's see if I can get her done. So why exploded? Well, it turns out what I didn't tell you is that uranium rods are coated in zinc. Yeah, that's just the way they do it for some other technical reasons. And what happens is the zinc, Zn, gets warm and reacts with water. So when it gets too hot, when the fuel gets too hot, the problem is not the radium, it's the zinc. So check this out. Here's my reaction. Zinc reacts with water, H2O, and it oxidizes, and I get ZnO. You might have heard of things oxidizing last year, like rust is an oxidized iron compound, okay? Well, look what happens. Eventually, this thing breaks down the water, and I get H2 gas forms. H2 gas is not a good thing. That's our problem. Anybody hear of a Zeppelin called the Hindenburg? It was filled with H2 gas. H2 gas is highly explosive. And that's what blew up at Chernobyl and at Fukushima. So I'll say it's highly explosive if heated. And guess what? It was heated. It'll probably be used to run cars someday. It can be used safely, but not if you heat it up, like in the Hindenburg Zeppelin back in the 1900s, or in both of these power plants. Whew. 1 minute too late. Sorry about that. Thanks everybody for hanging on. Really good discussion today. Thanks everybody for being there. I'll try and meet you again, I think, on Friday is the next time we can meet. So be well and stay healthy, and we'll see you again soon. Bye-bye.